Hello? Okay. So today I'm going to present a topic or presentation called topology optimization and JMP, although I actually did not use JMP to make any of the stuff in this slide. But it's more about the future of what I'm planning to do. And originally I wasn't planning to come here, but Miles told me you can come and just present what you have. So here I am. And so first, some introduction about me. I'm a first-year PhD student. So as much as I'm going to present today, I'm still in the learning stage. So kind of like some of the questions might be too advanced for me, but I'm trying to get there. And I work at this multidisciplinary design optimization lab. I have some background in mechanical and industrial engineering. That's where I got my optimization knowledge from. And currently, I'm interested in combining these two fields, mechanical engineering with optimization, by doing this so-called topology optimization. So I'm interested in the algorithm side and the modeling side, but also in scaling it up to hundreds of millions of variables. And I'm also doing the GSOC project these days, and I developed some eigenvalue solver, and I'm doing some buckling analysis work. So my focus in topology optimization is really about structure design. So let me first define what I mean by structure design here. So we have this design space, or like initial shape or initial design, and we have some requirements in the terms of boundary conditions. So these are rollers, and the shape is not allowed to move sideways here. It's not allowed to move up and down there. And we have some load. And the idea is to try and minimize or maximize some objective or multiple objectives and have some constraints that can be satisfied. And so what we might end up with is something that looks like this, which is given to us by the optimization algorithm. This may have been figured out by a mechanical designer who sits down on the problem and tries to solve it. But then when you increase the complexity of the problem, it may be much more difficult for the mechanical designer to do that. But the optimization algorithm can, or at least should. And so there's different types of problems that can be formulated. They can vary by the variable type. Most of the time the variable is binary because you want to find out which element has material and which element does not. But some problems, especially 2D problems, can also have a continuous variable that has a significant meaning, which is the sheet thickness. If you have a sheet and you're trying to decide on the thickness of the sheet at every point, then the sheet thickness here can be a continuous variable. And so this is a relatively easy problem. If you have, but most of the time we have binary variables. We can have different objectives, something called the compliance, which basically refers to the average movement of the whole structure, subject to some load. We can have some volume minimization if you want to minimize the cost of the design, stuff like that. And constraints also, a wide variety of them. And I'm going to present 3 specific examples in the next few slides. Mechanical systems can be many, so this will affect the analysis, so the way we do finite element analysis and the way we compute derivatives of constraints and objectives. Loads can be single, multiple, static, dynamic, deterministic, or stochastic, or most interestingly, there's design dependent or design independent. So if I choose to make a hole in the middle and it's actually submerged underwater, then there will be hydrostatic pressure applied. And so the modeling challenge here is, there's also some modeling challenge. It's not just the algorithm. So to kind of give you an overview of the field, I wanted to summarize it into pipelines. So the first pipeline is what the user has to go through in order to use this kind of technology. And so the first thing that he has to provide or she has to provide is an initial design in mesh form and some boundary conditions, pretty much what we were shown earlier in the figure. And this can be defined programmatically or through some standard file for simulations. It's called IMP file, which I created a parser for it so that I can read the problem right into Julia. And then the user might want to select some objectives, some constraints, and then it goes through one of 2 pipelines for topology optimization. These are commonly called the nested analysis and design and the simultaneous analysis and design. So the nested analysis and design, what it does is you basically have the top level, you choose the material distribution, and then at every stage to evaluate the derivatives and the gradients of the objective and the constraints with respect to the decision variables, we need to do some finite element analysis. And this enables us to compute these derivatives. And so we provide the 0 order and first order information to the solver, and then some optimization magic happens and we go back and repeat. So it's a nested framework in the sense that the analysis variables, like the nodal displacements, for example. So if you want to analyze this, we have if every node is moving by a certain displacement subject to the load. And so this is all hidden away. This is treated as a function of the decision variables. And we only have the decision variables to worry about, which are the material distribution. On the other hand, the simultaneous analysis and design, what we end up having is this analysis equation, for example, where U is the nodal displacement, will be used as constraints. And so we have a much bigger optimization problem where we have the decision variables, which are the material distribution, but also the analysis variables. All of them are treated as decision variables. But the advantage of this, according to some papers, is that it exposes more structure in the problem, as we will see, and that enables some better solutions to come out of it. Even though we can end up with 10 times bigger the problem size. This change is can easily blow up your problem size. But we also have one single pass, and the finite element analysis is done implicitly in the optimization solver, so we don't do it explicitly outside. So just some examples, we're not giving abstract concepts here. So this is called the volume constraint compliance minimization. We have some volume constraint, where VE is the volume of a cell or an element, and XE is whether or not we choose to add this element to the design. And C here is the compliance, which is a function of U, the nodal displacements, which is evaluated by this analysis here, analysis equation. And K is assembled from the so-called element stiffness matrices, and K is very sparse and known, I know the sparsity pattern and it's fixed throughout. And so the analysis constraints or equations are these two basically, and the design is the objective and that one. And so that's one example of a topology optimization problem. The second interesting example is this stress constraint volume minimization. So I may want to minimize the volume of a design, but then if I remove too much material, then this structure might fall because the stress is too high and the material starts deforming. So I have this yield stress, which is the threshold basically that I cannot exceed. And this is so-called the von Mises stress, which is a stress summary figure or summary number computed from the so-called stress tensor. And the stress tensor is basically just a linear function of the nodal displacement U. And so we have sigma ij here is a linear in U. The von Mises stress squared is actually convex in U, because this here is just a sum of quadratics, and each one of those is a linear function, and so it's convex in U. And so this whole constraint can be converted to, I should probably use one of the, So this whole constraint can be converted to this constraint, which is biconvex in U and XE. Also. The third problem that I'd like to present is called the buckling constraint volume minimization. And the most interesting constraint is this one here. It's a positive semi-definite constraint, where I have K and K sigma. K is just a linear combination of constant matrices where the weights are decision variables. And K sigma is unknown. It's actually it's bilinear in U and X. And so this is one very common problem as well that is solved in literature. And the challenge really is how to mix and match all these stuff. So I can minimize the volume subject to this constraint, but also subject to a stress constraint. And perhaps I may want to limit the movement of, limit this compliance to a certain value. Or even just a few nodes, I may want to make sure they don't move too much. And so mixing and matching all this stuff is where it really gets interesting. So just a helicopter view of the algorithms. This is a heads up of all the acronyms I'm going to use in the next slide. So most importantly, perhaps, is mixed integer, nonlinear, and semi-definite programming. So this one has integer, has continuous variables, and it has nonlinear and semi-definite constraints. This one is integer nonlinear. That was the most suitable name, I guess, for it, because it doesn't have continuous variables, but it still has nonlinear constraints and some definite constraints in the formulation. That's just nonlinear without any integer. And these are two specialized algorithms that are developed in topology optimization literature. This one relies on some nonlinear approximation of the integer constraints, basically. And these two you met before. So that's sort of an overview of what is usually being done in literature, where you have, first of all, single or multi-objective. The vast majority of papers are doing single objective. Some of them have been doing multi-objective. You have exact, you have heuristic. With exact, you can have the simultaneous analysis or the nested analysis, and this one just adds the continuous variables, which are the nodal displacements or the analysis variables. These are continuous. This one only has the integer variables, which are the binary variables, actually. Heuristics, you can also do the SAND, you can do the NAND. Green is basically the things that I've tried and that I've implemented, and that I will show you today in the demo at the end. And so with the simultaneous, you can do the incomplete version of the exact. That's one way to do it. Or you can just approximate the binary variable. Usually what they do is they make it continuous and then they raise it to some power. And that kind of pushes the values between 0 and 1 towards 0. It's not proven to converge except for one class of problems, but that's the common technique used there. And so they just convert the binary variables to some x to the power of p sort of form. And with the N, A, and D, there's some specialized algorithms that are developed. This one uses this power idea, and it uses the adjoint method for the N, A, and D to differentiate through the analysis equations instead of basically using du or the nodal displacements as decision variables. BSO is basically a binary gradient descent algorithm that removes elements and adds them based on some gradient information. And so you see here, there's a lot of jump potential. It's like screaming mathematical programming here. And much of this, as far as I know, has not been fully discovered or researched yet. Only one problem that I know of has been solved by an exact method, because it's known to be a mixed integer convex program. And it's been solved by the branch and cut method, I believe. So why am I here? That's a question you might have in mind. And so first, I kind of want to give a wish list, or what I want from the Julia optimization community, which I'm part of. And if it's not already there, if you have something similar, you can come and talk to me. If you don't, then I guess I can just work it out myself in the future. And so I'd like some framework where I can do continuous and binary variables. I have block constraints, because some of the constraints are very expensive if you want to do them one by one. Like the stress constraints, for example, it's easy to evaluate all the stresses at the same time. But if every time you ask for the stress in one element, I have to compare the variables and see if it's already computed or not, and then give it to you, then this becomes quadratic complexity. And so if I can give it to you all at once and you can manage yourself, that's linear complexity. And so I need block constraints, and the Jacobian should have a fixed sparsity pattern that I can specify. I need bilinear, biconvex, and nonlinear constraints. I need some conic constraints, most importantly the semi-definite and second order conic constraints. I need some partial structures, so some bilinear, some biconvex. So any pure algorithm is not really going to be helpful, because I want to have mixing and matching of all these stuff. Most importantly, and probably the most difficult, is the linear time and memory complexity, because I can have up to hundreds of millions of variables. And so it can easily just blow up any even group of machines, not just a single machine. It needs to be numerically robust to scaling. This point was not there before until it actually bit me recently, so I'm just adding it there, because sometimes when you add too many numbers, the errors can surprise you. It needs to be scalable, the whole pipeline, preprocessor and solver, using GPUs, using some distributed programming. And it needs to handle single and multi-objective, might as well. So is that possible with Julia's optimization ecosystem? I have no idea, but I hope I'm going to try and make it possible, I guess. And what I can offer right now is nothing but prayers, but after some paper submissions in the GSOC, I'm hopefully going to work and do some more coding on this. So let me just show you some demo real quick. So this demo is basically the green stuff that I was showing you here. Okay.
It's the other tab at the top.
Yeah, I can see that. So this is the problem that you saw. It's basically, this is commonly known as the half MBB. MBB stands for some fancy beam name. And it looks like this. This is the initial design. We have the load, we have some rollers here, and that's the initial design, what it looks like. And so what you can do is basically define a problem here of this sort. This is a rectilinear problem. It's easy to define programmatically. More complicated shape will have to go through the IMP file thing. I can visualize it with Mackie. This is only less than 1 week old. I kind of bugged Simon on the Slack until he made it work on my machine. And so yeah, that's what the initial design looks like. Then I can make some finite element solver. This finite element solver is important to compute derivatives when you're doing the NA and D framework. So we can have some displacement finite element solver that computes the nodal displacements, or we can have some eigenvalue solver that does buckling analysis. And so to do the buckling constraint, we need to do buckling analysis at every single step to compute the derivatives. And so I have to make some finite element solver, and I dispatch on the properties or the trace, if you like, of this solver. So there's displacement, or hopefully eigenvalue, or buckling. There is direct or conjugate gradient, and for conjugate gradient, there's assembly-based and matrix-free method. So all of these are supported. Then I can create an objective and a constraint. And the key point of all of this really is to show you this line here. So as soon as I create this objective struct, I can just call it at a certain x and given a certain gradient, and it will fill out this for you. And so from an optimization point of view, you don't have to know anything about finite element analysis except the interface. And this is really the interface here. And the same thing for the constraint. So that makes it quite easy here. Next, I have to make some MMA optimizer. MMA stands for the method of moving asymptotes. It's a nonlinear programming approach that is the most popular one in topology optimization. And it's implemented separately in MMA.jl that has nothing to do with the JUMP community. It's implemented by Christopher from Sweden. So I try to support arbitrary precision to the best I can. And this is how you call the algorithm. This is the SIMP algorithm. And then you can just get some final topology, which looks like this, for example. And similar thing can be done for the other algorithm, which is a binary gradient descent algorithm. You get a slightly different topology at the end, but that's what happens. And as you can see here, so this was a 60 by 20 grid, so that's 1200. And so the constraint was 50% of the 1200 should be there. So as you can see, this is the volume that we get out of it, which is 600. And it took 55 function evaluations, basically 55 finite element simulations to do that. I have a very similar problem. It's just a cantilever beam where you have, it's completely fixed from here, and then there's a load on the other side. And this is what you start with, and this is what you end up with. So also pretty, maybe surprising, maybe not, depending on your background. But that's pretty much the idea. That's my current state, and I'm moving forward, but on my own, so it might be pretty slow sometimes. But thanks for listening in. If you have any questions or suggestions, please talk to me after, or now. So, thank you. Please.
Can you tell me about your finite element solver? Is it in Julia? Is it
In Julia, JuoFem. It's using JuoFem.
Okay.
Actually, I have it on the extras. So I implemented a few packages, but most importantly, I'm just using JuoFem for the finite element. I added a bunch of stuff in there, but nothing significant. And yeah, so that's basically what I'm doing. So for finite element analysis, I'm using these 5 packages. For optimization, I'm using Optim, MMA, and for visualization, I'm using Plots and Mackie.
And so how long does the finite element solver take?
Majority of the time, 80% at least.
But how many, or like the simple problem that we're talking about?
Oh, for this problem, 2 seconds. Less than a second, maybe. Yeah. But if you blow it up to like 100 million, then it can take quite some time.
Someone else have you noticed?
So is there a version of this problem when you answer like macro elements that's in the, like macro elements like steel beams, just like steel beams? Because it looks like that's kind of what the designs are recreating.
Right. What do you mean, like?
So like could your decision variables are whether I put like a dollar for cement or steel or whatever in this particular location, like this grid element, could you instead of like try to like place like beams that are
Right. So there is different kind of branches of this whole field. Like generally you find as like shape or topology optimization, sometimes called sizing optimization. So maybe what you're referring to is like the length of a beam or something. So, well, let me just say what I understood anyways. So in general, we have an initial mesh, they call it the ground mesh, and this can be any shape you like. And if it's 2D, then I guess you can consider it sort of a beam, but if it's also in 3D in a certain shape. And so it can be any shape you like, as long as you can parse it and you can just have different elements. And the elements can be of all the common shapes, like hexahedrons, tetrahedrons, triangles for 2D, quadrilaterals for 2D. So it's very flexible, and if you can define it as loads, boundary conditions, and initial design, then I can solve it, assuming the solver can manage. So, yeah.
One more question, please. One of the constraints I think might be missing is manufacturability.
True.
These interesting shapes, and how are you going to make them?
True, and there is one way to kind of, I'm not sure if that makes it like extremely manufacturable, but some people try to enforce a minimum feature size, so it doesn't get lower or less than 3 millimeters or 5 millimeters. That way, you know, whatever manufacturing tool you're using can get in there and do its job. But there's a lot of research in that, but I have not fully read about that, so I cannot really answer it properly.
I guess you can always 3D print anything. That's all thing.